It's 9 o'clock, so let's get started. I'm going to talk about the science of climate change. The reason for that is as follows. This is an economics class, right? So most of it will be economics, but there's two reasons to start with the science of climate change. One is you can't hope to solve a problem unless you understand the problem and you know the basic mechanics and the stylized facts of that problem. So that is why we start here. And the second reason is that many people know something about climate change, but most people are hopelessly misinformed about climate change. You can read any amount of nonsense about climate change on the internet and in the media, even supposedly high quality publications such as The Guardian or the BBC or The Economist nowadays just stop nonsense about climate change. So that is why I start here, just to put us all sort of on the same page with a common understanding. And when I mean any amount of nonsense ranging from that climate change will somehow mean the end of planet Earth, right, on one extreme, and there are really people who make that claim, all the way up to climate change is a Chinese hoax, right? A, climate change is not a hoax, and B, the Chinese had nothing to do with that. And you can find any amount of nonsense in between, right? So that is why we start with, let's just talk about the science for about an hour in 3 steps, the enhanced greenhouse effect and observed climate change. I'm going to talk about general circulation models, and I'm going to talk about projected climate change. I don't need the full 2 hours for this, so I'm also going to make a start with scenarios and not with the technical options for emission reduction. You'll be listening to me this week and next, and then Diego, who you met yesterday, will take over. Don't ask me why. There are nominal reasons that I don't understand. I know does Diego fully understand why. But I'll be here week 1 and week 2, and then I'll be talking about impacts and adaptation. So I'll be doing all the non-economicsy type of lectures. So let's start with basic observations. On the left for you guys, you're looking at the 3 most important greenhouse gases, anthropogenic greenhouse gases. Anthropogenic means man-made. Anthros is man, not man and women, it's the man who did it. CO2, methane, nitrous oxide. And you're looking at the atmospheric concentration of these gases over the last 10,000 years or so. So this is since the start of the agricultural revolution. What you see is that it's been mostly flat, and then at the very end, towards the present day, these concentrations start to what looks like skyrocket. And the smaller insets, you're looking at the concentration since the start of the Industrial Revolution. And there you see it's not skyrocketing, it's merely increasing exponentially, right? So that is one set of observations and reconstructions and things like that. Obviously, way back when, people did not know what CO2 was or methane, and they did not know how to measure it. So the older data are obviously reconstructions. Then on the right-hand side, you're looking at 3 other graphs. The global mean surface air temperature, annual average, global average sea level rise, and snow cover in the northern hemisphere. Sea is going up, temperature is going up, and snow cover is going down. And this set of pictures is fully consistent with one another. This is exactly what we would expect. And the reason for that is the so-called greenhouse effect and its enhancement, right? The greenhouse effect works as follows. This is a cartoon not drawn to scale. This is planet Earth, and this is the Sun, which is much larger and much further away than this picture suggests. So the Sun sends out energy. It's a big nuclear fusion reactor. Sends out energy. Most of the energy ends up in outer space. A small fraction actually hits planet Earth. Some of that is reflected back at the top of the atmosphere. Some of it is reflected at the surface of the planet. But some radiation, some energy is absorbed by the planet. Right? That is the starting point. Now, that cannot be the end of the story. If the planet would just be absorbing energy and absorbing energy and absorbing energy, it would have evaporated billions of years ago, right? So the Earth must somehow get rid of this energy. Now the Sun makes light, as you will have noticed, but the Earth does not. It gets dark at night, the ground does not light up. If it does, you have smoked something that perhaps you should not have. The Earth emits radiation in the infrared part of the spectrum that is invisible to the human eye. And that is going out here. Some of it is bent in the atmosphere, but some of it, and that is where greenhouse gases come into play. A greenhouse gas is a gas, obviously, and by definition, a greenhouse gas is transparent to visible light. That is, if a ray of solar energy hits a CO2 molecule, it passes right through, but it's opaque to infrared radiation. That is, if a ray of infrared radiation hits a CO2 molecule, it is absorbed by that molecule. Again, that cannot be the end of the story. Because if CO2 molecules just keep on absorbing energy and absorbing energy and absorbing energy, they would have long ago fallen apart. So that CO2 molecule gets excited, as chemists would say, when it absorbs infrared radiation. But then a little while later, it re-emits this energy again in the form of infrared radiation. But the crucial point here is that some of that re-emitted infrared goes into outer space, some of it goes sideways, and some of it comes back to Earth, right? So on balance, because there are these greenhouse gases in the atmosphere, it is easier for energy to enter the planet than to leave it. And that means that there's more energy stored on the planet. I mean, it's still the case that on balance we emit as much as we receive, right? Because otherwise the planet would have evaporated a long time ago. But it's easier to receive energy than to get rid of it. So on balance, more energy is stored on the planet, and therefore it is warmer than it would have been without these greenhouse gases. Now, people reckon that the greenhouse effect adds about 33 degrees Celsius to the temperature of the atmosphere. So the average temperature of the planet is around 15 degrees, or used to be 15 degrees. Without greenhouse gases, it would have been minus 15 on average, which is probably too cold for life to have evolved, right? So that is the natural greenhouse gas effect. Now, this is very old science. The basic radiative properties of air were discovered by Jean-Baptiste Fourier, better known for his reform in 1827. And that's almost 2 centuries ago. The idea that it was CO2 in the air was published in 1854 by Foote. People paid a lot of attention to that particular paper, not because of its findings, but because her first name is Eunice, and she was a woman, and what the woman doing presenting to the Royal Society, right? So that is what attracted attention. And then 2 years after Foote's work, John Tyndall worked out the essentially the mathematics and the physics behind it all. Foote was an experimentalist. He discovered that CO2 did this rather than just air. Now, these experiments go back 150, 200 years. There's plenty of videos on YouTube, if you don't believe what I'm saying, if you don't believe what they have done, that you actually can recreate their experiments in your kitchen to show that, yes, CO2 really heats up. Really heats up things. So that is the natural greenhouse effect. Then in 1897, Svante Arrhenius published a paper saying, well, we're putting more CO2 in the atmosphere, and therefore it should get warmer based on first principles, right? So this is really, really old, really basic science. So the pictures that I just showed and the pictures that I'm showing now are fully consistent with one another. We're seeing CO2 concentrations go up, we're seeing methane concentrations go up, we see concentrations of nitrous oxide go up, and we observe the temperature going up. This is the temperature over land, this is the temperature of the top layer of the oceans going up, this is the air over the ocean is going up. Sea level is going up, sea ice is going down. This is the temperature higher up in the atmosphere. This is the temperature deeper down in the ocean, it's going up. Snow cover is coming down, and these are glaciers, and they're also melting, right? And then an important thing here in the middle is that humidity is also increasing. Now, humidity is important for, this is another symptom of climate change. Warmer air by Clausius-Clapeyron can contain more water vapor. So you would expect humidity to go up. So that is one thing, one reason why this is here. The other reason that this is here is that I spoke about these greenhouse gases, and I said they are the most important greenhouse gases, and then I corrected myself. I said the most important anthropogenic greenhouse gases. Water vapor is also a greenhouse gas. What we have here is immediately a positive feedback. That is, if you have more CO2 in the atmosphere, then the temperature is going up. If the temperature is going up, you have more water in the atmosphere. But because water is also a greenhouse gas, temperature is going up further, right? That's the first complication that we have here. But it's the first principles, I think, are beyond dispute and reasonably simple to understand. Even though there are people out there who try their best to make you confused or try their best not to understand. So let's start looking at the tools people are using to actually study changes in climate. And these things are called general circulation models. And the reason that we need general circulation models rather than the simpler methods that go back to Arrhenius, 1897, is because the story is a lot more complicated than what I just suggested. This graph from the sixth assessment report of the Intergovernmental Panel on Climate Change, and those are words that will be used a lot. It's essentially a body of the United Nations that every so often comes together and writes a big literature review of the state of climate science. And it's the Intergovernmental Panel on Climate Change, or the IPCC. Observed warming, and here are the different contributions to that warming. Observed warming between 1850 and 1900 is about, between 1850 and 2020, right? Relative to 1850, 1900. The Earth is warmed about 1.1 degree. And there's uncertainty in that measurement. Of course, that is what you're seeing here. And here we're looking at the various reasons why. So total human influence is about this, that the well-mixed greenhouse gases, CO2, methane, nitrous oxide, contributed about 1.5 degrees. Then there are aerosols, other stuff going on that actually led to a cooling effect. There's also natural things that happened. The sun is not constant, right? Constantly changing how much energy it actually emits. But over the last 150 years or so, that has not done a whole lot. It's done a little bit, but not a whole lot. Volcanoes put a lot of dust in the atmosphere that cool the place down, but also over the last 150 years, we've not seen that much volcanic activity, and definitely no increase, if anything, a decrease in volcanic activity. And then there is, because it's a large non-linear dynamic system, we also sort of are still responding, or the climate is still responding to things that happened thousands of years ago. It's a very conservative system. But also that cannot really explain what we have observed over the last 150 years. So these are the well-mixed gases, carbon dioxide, methane, nitrous oxide, and these are the relative contributions. HFCs we won't be talking about. We do start at 9. And then there's a whole bunch of other things that are going on. We've been burning fossil fuels, and if you do so, you emit sulfur, you create precursors for nitrogen, as well as for ammonia. And those things are sort of particles that swim in the atmosphere, and some of them interact with the climate in the sense that they directly reflect sunlight back into the atmosphere. You've all seen pictures of haze, right? And if it's hazy, then it gets colder, right? So that is going on. They also help in the formation of clouds, and obviously cloudiness also affects the temperature, right? So these things actually have cooled the planet. Then we have been dumping a lot of sort of black stuff, black carbon, mostly in the form of soot, and a lot of it ended up on what used to be white snow, but because of all the dust that we put in, all the soot that we put on, it's now gray or sometimes even darker snow. And as you know, if it's very warm outside, what you should be doing is wearing light clothes because they reflect the light and keep you cool, whereas if you go out and wear black in summer, you actually get much hotter. The same is true if you put soot on snow. So that actually leads to heating. Then we have changed the surface of the planet quite substantially. Basically what we've done is we replaced forest with grassland, essentially to put cows on and drink milk, but mostly eat meat, right? That is why most of this has been done. Now, if you look at a map, typically grassland is light green and forest is dark green. If you look down from an aeroplane, then pasture land is fairly light green and forests are fairly dark green. So again, if the color is darker, it absorbs more light, so that leads to cooling. Just explain why it leads to heating, right? So they must be thinking of something else here. And then there is the aviation contrails, the sort of the white clouds that you see high up in the atmosphere if a plane passes by. So there's all these things going on, and that just makes it a very complicated system. It is not just what Arrhenius said, more CO2 in the atmosphere, more water vapor in the atmosphere, and that's it. There's all these other things going on that need to be put in the model. The whole system is big and dynamic. I gave you a very basic radiative picture earlier, but there's all sorts of things going on. So here is the solar radiation coming in again. Parts of it gets bounced back, parts of it get absorbed, and so on and so forth. This is the outgoing radiation, and parts of it gets absorbed, and parts of it gets put back. Then we have evapotranspiration. It's essentially plants absorbing water and plants evaporating water, what physicists call latent heat, and there's that energy flow there. And then there's the thermals, that is essentially upwelling air, where you take heat from the surface, from the lower parts of the atmosphere to the upper parts of the atmosphere. And all these things are going on. And if you look at these numbers, right, 80 for latent heat, 17 for thermals, 161 here, 396 here, and 333 here. You see that these numbers are very big, right? Compared to the net change in radiative forcing, that is actually due to humans putting CO2 in the atmosphere and making this, or these two things bigger. That's actually only 1 watt per square meter. So there's all these things going on, but then the net change of human action is only 1 that is 2 orders of magnitude smaller than some of these radiation flows, energy flows that are going on. So we're changing the system only by a tiny little bit, but because there is no counterbalance, we actually have a large cumulative effect. Come in, we start at 9. Right? And in a proper physical representation of the atmosphere and what it's doing, you actually need to include all these things, right? The same goes for the carbon cycle. This is again a picture from the IPCC, from the 6th assessment report. This has the latest numbers and awful colors, right? Really, truly awful coloring. It just hurts your eyes. So what is going on here? In the circles, we have stocks of CO2 measured as petagrams or billion tons of carbon. Then the arrows are flows, annual flows, again measured in billion tons of carbon per year. The yellow, I think it is the situation before the Industrial Revolution, and they call that natural. It's debatable, of course. And then the pink is, I think, is what has happened over the last 150 years or so. What has changed over the last 150 years. And what you see is that there's lots and lots and lots of things going on. So we have volcanoes putting CO2 in the atmosphere, we have rocks weathering, those are pretty small numbers. Then what we have here is essentially the terrestrial biosphere. So we're about to enter fall, right? It's been unseasonably warm. But within the next few weeks, leaves will start falling from the trees and plants will start dying back, right? Now, these are essentially built from carbohydrates. So once they do that, they start releasing water vapor and they start releasing a lot of CO2, right? So that is this flux that you see here. And then in spring, which is 6 months away, they will start growing back, right? And start absorbing CO2 from the atmosphere again, right? So there's those fluxes that are going on, and the order of magnitude is about 110 billion tons of CO2. So that is going on every year, and this is a net flux annually because we have much more land on the northern hemisphere than on the southern hemisphere, so you actually see a seasonal effect here, right? Had we had the same amount of land on the northern and the southern hemisphere, then there would not be this sort of annual seasonal thing going on. Similar things going on in the ocean, whereas this is basically biology, plants growing and plants dying. This is a chemical thing. That is, if there's CO2 in the atmosphere, then by the laws of partial pressure, some of that CO2 will have to get absorbed in the waters that connect to that atmosphere that is in the ocean, right? And because this thing is going on, you also see a whole lot of fluxes going on in the ocean in the order of 55 billion tons of CO2 per year. So there's all these things going on naturally. And then what we have done is this stuff. We have cut down a lot of trees and replaced them with grass. That is less vegetation. That emits a substantial amount of CO2, 1.6 billion tons of CO2 per year. And we have our fossil fuels that we are burning, that we're digging out of the ground and burning, and that adds another 9.4 billion tons of CO2 per year into the atmosphere. And these things used not to be there, right? Now, there are some clowns out there who will say, humans, only 10. Terrestrial biosphere, 100. 110. The oceans, another 50. We are trivial, right? Net human emissions are about 5% of total emissions of CO2. So what is going on here, right? Why this fuss about climate change? Well, the reason is that there's humans emissions of 10, and then there's natural emissions of around 160, but then there's also natural uptake of around 160. But there's no human uptake of to compensate for the 10 that we put into the atmosphere every year, right? So again, the human effect is fairly small compared to all the things that are going on. But because there's no counterbalancing effect to what the humans are doing, or us humans are doing, I should say, the system slowly changes, right? And we see an accumulation of CO2 in the atmosphere. The pre-industrial concentration was 590, and we added 280 to that, right? So that is a substantial increase in the atmospheric stock of CO2. Talking a little bit more about these stocks, we have burned around 450 billion tons of CO2. That's the total amount of CO2 that we have taken out of the ground in the form of coal, oil, and gas and burned. There's a whole lot more to go, right? There's still about twice that in total, mostly in the form of coal reserves. Oil reserves are there, gas reserves. We add all that, burn all that, we have a long way to go still, right? So I said there's no counterbalancing effect to the human emissions of around 10. That's actually not true. There's no human counterbalancing. But actually, because we've put this the CO2 in the atmosphere, plants are actually growing faster and bigger and absorbing more CO2 than they used to. And similarly, around 2 billion tons of the 10 that we emit per year on net end up in the ocean. And in total, around half of our emissions are taken away by human nature in roughly a year. So the 10 that we emit, around half of that is offset by increased chemistry and increased biology, essentially. Right? But these things are fairly complex, right? And there's lots of things going on. Plant growth is obviously affected by weather and climate, right? The same goes for these processes in the ocean. They are essentially determined by ocean currents and those sort of things. So this is also depends on the climate. So we have yet another feedback, right? I've been talking about a number of feedbacks. So there's all sorts of things going on. Besides, we've added CO2 in the atmosphere, and therefore there's more water vapor in the atmosphere. There's all these other feedbacks going on as well. And therefore what we need are systems, models that do the best that they can in representing all these complexities in the system, right? Now, these are called general circulation models, or nowadays Earth system models. And they are the second most complex models built by humans. The most complex models are the protein folding models. The second most are the climate models. And they run on supercomputers. They are sort of operated by teams that measure in the tens of PhD scientists, sometimes hundreds of PhD scientists working on these models. They are big beasts, they are expensive, and they're extremely complex. And I don't think there's anybody who understands the whole of the model nowadays. And actually, there's whole teams of people working on trying to interpret the output of these things, right? So that is a bit scary, definitely to us economists who recall the 70s, which you guys don't, but I do. But we have some validation that these models are not completely crazy. And that is shown here again from the latest IPCC report. A lot of information on these graphs. What we're looking at is the temperature over land, over water, and this is the sea temperature, and then this is the temperature over land for, yes, for North America, Asia, the Arctic, Central and South America, Australasia, Antarctic, Europe and North Africa, this is where we are. And then I don't recall why. Oh wait, this is the temperature, and then we have sea ice here in the Arctic and the Antarctic. This is temperature in the Arctic and Antarctic, and this is rainfall. That's going on. There's three colors on this. In black, you're looking at the observed temperature. In brown, you're looking at the modeled temperature, and in green, we're also looking at the modeled temperature. And then if you have very good eyes, you see some sort of confidence interval around the brown and the green, which is not a confidence interval, but a range of model. So black is observed. Brown is what happens. What does the model say? Come in, we start at 9. What does the model say if we started in the year, this is very tiny, 1850, and let the model run to today, 10 years ago, and we put in everything that we think affects the climate. So volcanoes, changes in solar activity, changes in sulfur emissions, changes in CO2 emissions, and so on and so forth. And if we do that, we let the models run, and there's now about 30 of these beasts around, then actually from where you guys are sitting, the brown line and the black line sort of overlap. And it's actually at points very difficult to see the brown line. Here it's a little bit more visible. There's a lot of variation in the black line, and therefore you see the brown line appearing from behind the black line. But essentially, if we let these models run with all things that we think change climate, then we basically produce the observed record, right? So these models are not completely crazy, right? Then the green experiment is essentially the same set of models, the same run, start the model in 1850 and see what happens. But now without the human factors that we think affect the climate. And if we let the models run like that, we find the green line. And what you see is that, yeah, well, up to 1950 or so, it's actually difficult to tell the difference with and without human effects. But since the last, 30, 40 years, it's actually very difficult to explain the observed warming without human intervention. And you actually, if you have very good eyes, see that the brown confidence interval and the green confidence interval start to separate, right? Now, you may think, thinking back of your statistics class, that this denotes significance, which would be the case if these were independent observations. It's not true, it's the same model runs, right? And it would be true if this were a confidence interval, which is not. It's a range of model results. It's a range of best guesses. But it does suggest that, yes, it is very difficult to explain the observed warming without human intervention, which sort of suggests, yeah, it's us who did it, right? There's also a lot of statistical work that basically reaches the same conclusion. So that is one thing to take away from this, right? Yeah, it's us. And the second thing to take away is that these models are not completely crazy, right? They can reproduce the past, and therefore perhaps we can trust them on what they say about the future. So that is the last topic before the break. So if we let these models run in the past, and then just keep them running until the year 2100. Now, I will not be around in 2100, but chances are a good few of you will be, right? What happens, right? Global surface air temperature, sea ice, pH, I'll talk about that in a sec, and sea level again. And obviously, the main driver here are human emissions, right? And we don't know what human emissions will be. I will talk about that after the break. But here we have 5 alternative scenarios, 5 alternative ways in which the future may unfold in terms of the emissions that we put out from very high to fairly low. And what you see is that implies warming up to 5 degrees relative to 1850, but perhaps only 1.5 degrees. Right? But that is sort of the range of warming that we can expect. The additional warming that you can expect by the time you are very, very old, right? But perhaps still alive. Sea ice on the North Pole will disappear in 3 of the scenarios and fall very substantially. In the other 2, sea level will go up by up to 1 meter by the year 2100. And I'll talk about carbon. We start at 9. So that is something that these models tell us. Now, this is the change in the global average temperature, which is not particularly interesting or representative, because there is no reason whatsoever to assume that warming will be equal globally. These are the observed changes. This is, well, the models say, again, the models do not only do reasonably well in terms of the mean projection for the world as a whole, but also do a reasonable job in projecting the spatial pattern. And then here, so this is where we are a few years ago, 1.5 degrees of warming, 2 degrees of warming, 4 degrees of warming. And you see very distinct patterns here, right? The first pattern that you may note is that it warms faster over land than over the ocean. And this is very simply because of the greater heat retention of water over land. So, you guys live in Brighton, so you know about this, right? So you know about this anyway. So what happens? If you get into winter, it gets dark before it gets cold, right? And then in spring, actually, it gets light before it gets warm. And that is because the ocean, and the sea, it's particularly pronounced if you live near the sea, sort of delays the direct effect from the light, right? In summertime, the sea absorbs a lot of heat, and then in wintertime, it releases it back. Until it's come February, there's very little heat left to release from the ocean, right? So that is why sort of the astronomical and the meteorological winter and summer are sort of like shifted by 2-3 months, right? The same happens in a scenario of general warming. It's the land that gets most of the hit, that warms much faster than the oceans. So when people say 2 degrees of warming or 3 degrees of warming, they typically mean for the world as a whole. But of course, humans are not spread evenly over the planet, right? Most of us, almost all of us, live on the land, right? So we actually would observe more warming than the average, the global average suggests. The second pattern that you see that is robust, come in, we start at 9. The second pattern that you clearly observe is that warming is much more pronounced towards the poles than towards the equator. And this has to do with the way heat is transported through the atmosphere. We observe this and we see this in the models as well. So 4 degrees of warming global average means completely different things depending on where you live, right? Now, when temperature changes, and when temperature changes unevenly, then immediately pressure patterns change as well, right? Because temperature and pressure are very closely related to one another. If this warms faster than this, then you see your pressure patterns change, and therefore your wind patterns will change as well, because wind goes from high pressure to low pressure, right? So your wind, the force of the wind and the direction of the wind will change, and that means that the transport of water vapor in the atmosphere, clouds and droplets, also changes, right? So if the temperature changes, rainfall must follow. And you see that in this particular set of graphs. So brown means drying, blue means wettening. 1.5 degrees, 2 degrees, 4 degrees, you see very profound patterns, right? You see very profound patterns of change. Some places get wetter, some places get drier. The Mediterranean particularly would see a lot of drying. The fact that it dries over the ocean is of course of no consequence to us, sort of, but of course there's a lot of agriculture and a lot of people here. And in other places you see actually things getting substantially wetter. Now, this pattern is for the annual average. If you draw this map for the different seasons, you would get a different pattern again. And in the place of the world where we are, the forecast is actually that things would get wetter in winter and drier in summer. Again, this is a source of confusion in the media, because the forecast really is that we will get more droughts and more floods, right? And some people respond to that, you must be crazy, how can it be wetter and drier at the same time? That is not the forecast. The forecast is it will get wetter in winter and drier in summer, which is a particular problem in Sussex, right? Because we already have a problem with summer drought and we already have a problem with winter floods, and both will get worse. The forecast is not that it will get drier and wetter in the same place at the same time on the 3rd or the 4th of October. No, drier in summer and wetter in winter. This obviously matters for agriculture. Another pattern that you see here is that a lot of rain is sort of moved from the mid-latitudes towards the poles, right? This is sort of problematic because our agriculture is actually in the mid-latitudes, not towards the poles. And particularly in southern Africa, this is a problem. Because in Europe, essentially what happens is that the rain is pushed from the Mediterranean to Germany, France, England, right? In southern Africa, the rain is pushed from Zimbabwe, Botswana, South Africa into the Southern Ocean, where there's no agriculture, right? And the fish really don't care whether it rains or not. So this is a problem. This leads to net drying over land, which is where we get our food from, most of our food from. This is rainfall. What actually matters for agriculture is much more surface, soil moisture, sorry. And these are the changed patterns in soil moisture. This is actually plants don't drink rain. The rain falls onto the ground, gets absorbed into the ground, and then plants take it up, most plants. This is what matters. And you see again very distinct patterns of changes in soil moisture. If this is in the Sahel, we'll get a good bit wetter, which is good. North Africa will get a good bit drier. So this is a redistribution of agricultural production with all the problems that come with that, right? Rainfall, by the way, is extremely difficult to model. And that is because clouds are very complex and the physics of clouds happens at a very tiny scale. So it's very difficult to model this properly. So these patterns are sort of like, yeah, this is what the average model says or the median model says. But if you look across models, you actually see completely different simulations and completely different results. I have a smartwatch that tells me all sorts of everything, not necessarily what time it is. I talked a little bit about sea level rise already. These are the projections of sea level rise. I did not talk about the cause of sea level rise. Again, this is a source of confusion. The main source of sea level rise is expansion of water. Now, I see only one coffee or teacup. Coffee, I think. Now, that coffee is slowly cooling down and it is shrinking because of that, right? Now, you think that is nuts, right? Because you do not have less coffee than you had half an hour ago, apart from the stuff that you drank. The coffee in my cup does not, or the tea in my cup does not visibly shrink as it cools down. But it does really, right? Similarly, if the ocean warms up, it expands. Now you may think this is a tiny effect, and it is. The ocean waters expand by a tiny little fraction. The issue here is that the ocean is on average 3 kilometers deep. So if the ocean expands by a tiny little fraction, that is actually very difficult to observe, but you are not 3 meters tall, right? Then it actually, relative to your body size, it actually expands a lot, right? So that is the main cause of sea level rise. It is expansion of seawater. This is hard to imagine until you realize just how deep the ocean is, right? And we're talking about, by the end of the century, maybe 40 centimeters, maybe 70 centimeters, right? And it goes up, the uncertainty goes up to 1 meter or so. That's about here, right? If I were standing at sea level, which I'm not. Right? Again, the pattern is not homogeneous because there's all sorts of things going on, expansion of water, changes in pressure patterns, changes in transport, changes in gravity, and so on and so forth. So the pattern is not homogeneous. So some places will see more sea level rise than others. And then, of course, there's also the thing that most people think about when they think of sea level rise, that is ice is melting, and that adds to sea level rise, but not nearly as much as thermal expansion. And there are glaciers that are currently resting on land that are sliding into sea. And if they rest on land, they don't contribute to sea level. But of course, if they float on water, which is what they will initially do, they do sort of push up sea levels, right? So that is going on. There's two more things I need to say. I talked about rainfall already. I started talking a little bit about wind. So I said, well, if temperature patterns change, then pressure patterns will change, and therefore your wind patterns will change. No dispute there. We're not so much worried about wind, we are worried about storms, right? There the news is pretty bad. If you're looking at tropical storms, hurricanes, typhoons, that sort of stuff, there is probably no change in the area. I don't think we will see a hurricane in Brighton. There's probably also no change in the frequency of these storms. We will not see more of them. Actually, currently the projections are that we will see slightly fewer of these storms, but they will become more violent. That is, wind speed will increase. And that is exactly the wrong thing that we want, because the damage done by storms is actually linear or slightly less than linear in the frequency of storms. And that is, if you're hit by a storm, then all the vulnerable stuff has been blown away. And then if you're hit by another storm, there's actually less damage done by the second storm. So we actually worry less about the frequency of storms, but we worry more about the force of the storms, the violence of the storm. And one way to look at that is to say that the force that the wind exerts on the tree in front of your house or your house is the wind speed to the power 3. So a small increase in wind speed, maximum wind speed, leads to a large increase in the damage done. And unfortunately, that is what the current models say, that because there's more energy in the system, because gradients between the surface and the upper air and gradients between land and sea become larger, storms will become more violent. Now, that is true for storms in the tropics that don't bother us directly. It's also true for the sort of winter storms that hit us, the extratropical storms. They will also probably become more intense. Now, final thing, and then we're going to break. Ocean acidification. So it sort of popped up on a few slides already. If there's more CO2 in the atmosphere, then by the laws of partial pressure, there's also more CO2 in the water that connects to the atmosphere. Now, nowadays we call CO2 or carbon dioxide, right? Some people call it carbon, but that is wrong, because carbon sort of manifests itself in many, many different ways. We used to call this stuff carbonic acid. And there's some dispute over what carbonic acid really means. Is it all CO2 or is it just CO2 that is dissolved in water? But that doesn't matter because we are talking about CO2 dissolved in water. The operative word here is acid. CO2 when dissolved in water is a mild acid. Now, what does that do? Well, it increases the acidity of the water, right? Obviously. Now, what does that do, right? So, suppose you want to clean your shower, right? What you noticed, hopefully, is that if you don't do that, you sort of like get these sort of white traces in your shower. And that is because there's calcium in the water that comes out of the shower, and the water evaporates, but the calcium remains, stays behind. And those are the little white flecks that you see in your shower that will turn black eventually, right? The way to clean your shower or your toilet or your sink is to put a cleaning agent on. And if you study what goes into these cleaning agents, the active ingredient is always acid. Acid is the way to dissolve calcium, is the way to get rid of that stuff. Right? So what we're doing is we're acidifying the ocean. That is, we're mopping up acid. Now, that is no problem for you guys, or for me, right? Because it's a mild acid. And we are clever enough that our skeleton is on the insides of our bodies. So the calcium in our bodies does not come in direct contact with the seawater, so this is no problem for you guys. It's a mild acid, right? Not the sort of stuff that people throw at wayward girls, right? If you have your skeleton on the outside of your body, you're a mollusk or something, then you do have a problem, right? Because then your skeleton actually doesn't grow as fast, may actually start dissolving. Or if you're the White Cliffs of Dover or the Seven Sisters closer by, right? Those are made of calcium, right? Those cliffs will erode faster if more acidic salt water is sprayed on them, right? So that is where the problems lie. Now, you're all familiar with sort of the large calciferous species. So a whole lot of plankton, and sort of the stuff at the bottom of the food chain, has skeleton on the outside of their body and will not grow nearly as fast or not at all if the water gets more acidic, right? So, and of course, corals are also made of calcium, right? So that is where the problem lies with ocean acidification. Right? So, after the break, I'm going to talk about where do these scenarios come from, right? The different colors. We're going to break now and we're going to reconvene at 10 past 10. Okay, let's continue. Before the break, I talked about the science. After the break, there's a lot more chemistry and engineering, a bit of biology. I'm making a start on next week, so that essentially next week we'll have more time. This is not touchscreen, this is my thing getting stuck. Next week we have more time to talk about emission reduction options, which I think requires quite a considerable amount of time. Before I'm going to talk about scenarios, I'm going to talk about where do these greenhouse gases actually come from. This is the world as a whole for the year 2015. I think 36% of greenhouse gas emissions come mostly from power, also from making heat, 15% from manufacturing, 15% from transport. So these are the economic activities where it comes from. Residential worldwide is only 7%, and then there's a whole bunch of other things. Methane is 17%, mostly agriculture. Nitrous oxide, another 7%, also mostly agriculture. And then we have the specialized the industrial gases that we won't be talking much about, not because they're not important. It's 2% or so in total, but because they're a long list of very specific stories. But let's start with CO2, which, as you can see, is 3/4 of the story in terms of emissions. So the most important source of CO2 is the combustion of fossil fuels. How does this work? All of you have lit a fire at one point. So you take a log of wood, which is a carbohydrate that is mostly built of carbon atoms and hydrogen atoms. And then what you do with that wood is you add energy. You put a match to it. You add fire, right? That is, you add energy. Now, the energy that you add is enough to break the chemical bonds between the carbon and the hydrogen. Breaking chemical bonds takes energy. That is why you have to add fire. And then, because carbon and hydrogen do not like to be on their own, the hydrogen oxidizes, forms a new chemical bond with oxygen and becomes H2O. That is the water vapor that you sometimes see coming out of fire. The CO2 also oxidizes and forms CO2. Now, those new chemical bonds that are forming, C and O, H and O, that releases energy. And as you've no doubt noticed, once the fire is going, it releases more warmth than you initially put in, right? Now, this is important to realize because this is how we get energy out of fossil fuels. The source of the energy is the formation of the new chemical bonds, and therefore the energy that comes out is from making CO2. There's no way you can get energy out of oil or coal or gas without making CO2. And in that sense, carbon dioxide and climate change is a completely different problem than acidification, which comes from sulfur. If you burn coal, you also form SO2, sulfur dioxide, which leads to problems of acid rain and so on and so forth. But if you ask an engineer and you're saying, well, there's sulfur in your coal and that leads to SO2, the engineer will tell you, well, I'd rather not have that sulfur in my coal because actually it messes up my plant. It leads to all sorts of costs. It actually reduces the efficiency of my plant and so on and so forth. I actually don't want that. That is a nuisance in an engineering sense and an externality in an economic sense, whereas CO2 is an externality in the economic sense, but it's crucial in the physical chemical sense. You can't get the energy out of the fossil fuels without making CO2 because it's the making of CO2 that releases the energy, right? That's a very important thing to realize here. Now, not all fossil fuels are created equal. Peat, which is essentially very young coal, emits around 117 tons of CO2 per terajoule of energy. Coal, all sorts of gradations of coal. Standard coal around 95, petrol around 70, gas around 57, right? So not all fossil fuels are created equal, and one way of reducing CO2 emissions is to switch from one fossil fuel to another, right? Or you can actually also increase emissions that way, right? But that's not the idea. These are power generation in the United States between 2000 and 2020. This is the gas that went, the fuel that went in, and this is the CO2 that came out. And what you see happening in the United States is that because of the discovery of not shale gas, but ways of getting shale gas out of the ground, price of gas went down, price of coal stayed up, and you see a rapid substitution away from coal towards natural gas. And as a result, emissions have fallen quite rapidly in the power generating sector in the United States, right? So this actually is an effective way of reducing emissions. Stop burning coal, start burning gas instead. And in both cases, these are proven technologies. We know exactly how to do it. There is no technical reason not to do it. And the economics was such that, yeah, you would be silly to burn expensive coal if you have cheap natural gas. Now, this happened over a relatively short span of time. Typically, these transitions in energy use, in the change of the fuel that we use, are pretty slow. What you're looking at here is the worldwide consumption, wrong term, worldwide use of energy. This is muscle power, this is fuel wood, this is animal power, and coal, oil, gas, nuclear, and this must be renewables, right? Yeah, this is mostly hydro. These are totals. Here we're looking at the shares. The time scale is from 1820 to roughly today. And what you see is that, yes, we can completely transform the energy sector, right? We have done so during the Industrial Revolution, where we moved away from animal power, essentially, fuel wood to coal. And then we did it again by reducing the share of coal and replacing it with first oil and first gas. This can be done, right? But you also see that the timescales of this are actually fairly slow. And the reason for this is very simple. If you look at a gas-fired power plant, then the machinery in that plant has a lifetime of 25 years. If you look at a coal-fired power plant, then the machinery has a lifetime of 40, 60, sometimes 80 years, right? It simply takes a long time to replace all the capital because all this capital is long-lived, right? But it can be done over time, and it has been done, right? Repeatedly. So that is CO2, that is where CO2 comes from. There's also, I talked about it already, CO2 coming from land use change, chopping down trees and replacing it with grass, or burning down trees, more likely. Also, CO2 comes out of the production of cement. And again, this is intrinsic to the process. So what is cement? Well, cement essentially is limestone with some of the carbon removed from the lime. If you take lime, you remove the carbon, you have cement. And the way to get rid of the carbon is to dump it into the atmosphere in the form of CO2, right? So that is where that CO2 comes from. And again, there's no alternative, right? You can't keep this carbon in the cement, in the lime, because then it's not cement and it's useless essentially. Methane has a range of sources, but it's all the same chemical process. If roughly the same. So an important source of methane are cattle, or actually all ruminants, most ruminants. Cows eat grass, right, and produce milk. Let's keep it simple. Grass is a carbohydrate, milk is a carbohydrate. So where does the CO2 or the methane comes from? If you compare the chemical composition of grass to the chemical composition of milk, what you find is that both have C and H, but there's more H relative to the amount of C in grass than there is in milk. So somehow in the transformation from grass to milk, you need to get rid of your hydrogen, your H, right? That is what a cow does, essentially, in a chemical sense. Now, how does that work, right? H is actually a very dangerous substance. If you have free-floating hydrogen, it immediately reacts with oxygen to become OH, which is a radical, in the sense that it destroys anything on its way, right? So we don't want OH. We don't want hydrogen radicals. The second preferred path for hydrogen, if it's on its own, is to go to hydrogen gas, H2. So if you're a cow, you're eating grass and you're getting rid of your H, there's not a lot of oxygen in a cow's tummy, so it won't go to OH, it won't go to a hydrogen radical. It would then tend to go to H2, hydrogen gas, which is the stuff that keeps zeppelins afloat, right? That is also not something you want in your tummy. Right? So what cows, or rather the ancestors of cows, have done is they formed a symbiotic relationship with methanogenic bacteria. And what those bacteria do is they convert the free-floating hydrogen into CH4. That is, they sacrifice 4 dangerous hydrogen atoms. No, they sacrifice 1 useful carbon atom to get rid of 4 dangerous hydrogen atoms to form CH4 or methane, and then the cows actually burp that out. It comes out at the front, not at the end, as some people claim. So that is where the methane comes from. And again, this is basically intrinsic to the system. And just to understand how intrinsic, the ecological function of cattle is essentially to be large grazers, to keep grassland open and that sort of stuff, and then produce milk and meat in the process, at least from a human perspective. Animals that fulfill a similar role ecologically are kangaroos. But kangaroos do not produce methane. Kangaroos instead produce acetate. It's also get rid of a whole lot of dangerous hydrogen, and they poop that out. Essentially, in order to get rid of the methane emissions from cattle, what you need to do is re-engineer the cows to become more like kangaroos, right? In terms of their metabolism. That is how you get rid of methane, right? So it's fairly intrinsic. Of course, you can also eat less meat. That would help as well. The other 3 big sources of methane work the next 2 work in basically the same way. So if you have plant material that rots in an oxygen-rich environment, it goes to CO2. If you have plant material that rots in an oxygen-poor environment, it goes to CH4. So wet rice, the leaves drop, they fall into the water, right, into the paddy fields. There's no oxygen there, not a lot of oxygen, and therefore it goes to methane. Similarly, if you throw away your apple core and it ends up in a landfill, then it's covered with all sorts of other waste, and therefore there's very little oxygen, and therefore the organic material that you have thrown away turns into methane, right? This is fairly easy to solve. Well, we just saw the example yesterday or the day before, right? So if you have landfill, there's a lot of methane coming out. So what you do is you put a cap over it and you capture it, and then you store it in a tank, and then when lightning hits, you get this nice big explosion. So that is what happened in Oxford, right? So we know how to get rid of that. Methane coming out of paddy rice fields is a bit more difficult, right? Because you can't put a cap over your rice fields, because that would block, the cost would be astronomical. You would block the sun, so your rice doesn't grow. So no, we don't want that. The final source of methane is leakage, and that is something that I haven't told you about methane. Methane is CH4, and we call it methane when it's a nuisance. But if CH4 is useful, we call it natural gas. And the two are chemically identical. They're the same thing. It's just that one we like and the other we don't. right? If you're mining gas, but more importantly, if you're transporting gas, some of it leaks out of your pipes. And that is actually also a fairly substantial source of methane emissions. The solution is simple, right? Fix those pipes, but costly. Nitrous oxide, N2O. The main source here is the over-application of fertilizers. In order to make plants grow, we throw nitrogen on our fields, plants grow better. Some of that excess nitrogen that is not taken up by the plants ends up in the soil, reacts with other things that are going on in the soil, and that turns into nitrous oxide. Nitrous oxide, not nitrogen oxide. This is laughing gas, right? So that is now a Class C drug for some reason in this country. It's the same stuff, right? It's completely innocent. Your voice goes funny and you see funny things, but it's completely innocent. But we have a very conservative government, so we banned this innocent pastime. It's the same stuff, right? It's actually better in your lungs than in the atmosphere, because in your lungs it just makes you do and see funny things, whereas in the atmosphere it actually warms the planet, right? Anyway, I did not tell you to use drugs, right? So that is where the stuff comes from. Now, where is the stuff going to? For that, we will use the so-called Kaya identity. And the Kaya identity works as follows. I'm actually going to first look at past emissions. What we're looking at in this picture is global CO2 emissions from fossil fuel combustion from 1965 to the year 2021, I think. And the black line are emissions. Everything is indexed so that 1965 is 1. And what you see is that CO2 emissions have more than tripled over this period, right? Now, you may ask, how come, right? This is a good question. Now, for that we use the Kaya identity. Kaya identity says that emissions E are equal to the number of people P times per capita income Y over P times the energy intensity of the economy X over Y times the carbon intensity of the energy sector E over X. Now this is an identity, right? This is true. P cancels against P, Y against Y, X against X. So essentially this equation says E equals E, right? And we can all agree that this is true. All identities are true, some are useful, and this identity happens to be useful. So if you want to know why did emissions triple, you can just break it down in these components. So the blue line here is the number of people, which has increased by 2.4, a factor 2.4 since 1965. So emissions have increased faster than the number of people, right? So there's higher emissions per capita now than there used to be. In the orangey color, you're looking at per capita income, which has increased by a factor 2.5 over this period. So the total economy has increased by a factor 5 roughly, right? The product of these two, sum of the two. So the total carbon intensity of the economy has fallen, right? Emissions have increased by a factor 3.5, the economy has grown by a factor 5, roughly half, per capita income roughly half the number of people. So the carbon intensity of the economy has fallen, right? Over this 55 years, no, 55 years period, right? Doing that right? Yeah. Why has the carbon intensity fallen of the economy? There's two reasons here. One is the carbon intensity of the energy sector, the other is the energy intensity of production. And what you see is that over this period, the energy intensity, so this is the amount of energy we use to produce $1 or £1 of value added. That's the energy intensity. That has fallen from an index 1 to an index 0.6. That is, it has improved by 40% over this period. The carbon intensity, that is how much carbon do we emit per joule of energy used, has fallen by less. Now it's sort of stagnant for a while, then it fell a bit, then it was stagnant for a while, then it went up, and now it's falling again, right? The sort of drops that you see here are essentially the oil crises of the 70s. The rise that you see here is essentially the growth of first the Chinese economy and then the Indian economy. It's basically coal driven, right? And now they're switching to gas, they're switching to renewables, just as we are doing. And that is why the carbon intensity is coming down, right? So this Kaya identity is a neat way of understanding, of decomposing the growth in emissions in the past, right? It's no longer emissions and they come from somewhere. Now we have something that we can talk about and think about, right? So this is relatively straightforward for the past. There's a lot of data that goes in, but of course we're not so much interested in the past, we're interested in the future. And if we want to generate these emissions scenarios, that will tell us, will it get 1 degree warmer or will it get 5 degrees warmer by the end of your lifetime? Of course, what you need to feed into these general circulation models are emission scenarios, right? You need to put in future emissions. And that is what is going on in this picture. And essentially what you need to do for such an exercise, if you want to know how warm will it get by the end of the century, you need to answer the question, how many people will there be? How rich will they be? How much energy will they use? And what sort of energy they will use. And then you've done part of your CO2, right? And if you then want your methane, you need to say how many people will there be? How rich will they be? How much waste will they generate? What will they do with that waste, right? How many people will there be? How rich will they be? How much meat will they eat? And what sort of meat, right? One thing I did not say is that there's also a big difference in methane emissions between cows and chickens per kilogram of meat, right? Right, so that is what we need to do. And not for 2025, right, but for the year 2100. Or actually a bit beyond that. And you can understand that this is a difficult thing to do, right? You've all done your macro, so you know about economic growth models, right? And that they are not necessarily good at forecasting, but this is what we need to do, and it's a good bit more complex than your standard macro problem. So a few brave souls have actually done this, and what you're looking at here is the latest set of scenarios that are used by the Intergovernmental Panel on Climate Change, the IPCC. These scenarios are called SSP, Shared Socioeconomic Pathways, and there's 5 of them, and they're imaginatively called SSP 1, 2, 3, 4, 5, right? And the different colors are the different scenarios, and they're here broken down in the Kaya identity. But the first thing we're looking at is population. And essentially you see 3 scenarios there. And we're currently here. According to one scenario, the world population will go up to 1.3 billion by the end of the century. No, it'll go up to 13 billion by the end of the century and continue to increase. According to the other scenarios, they will sort of like reach their max around mid-century, and one group of scenarios falls, the other stabilizes. And in this scenario, population actually goes down. World population goes down from the current 8 billion, almost 8 billion, to something like 7 billion. And this is a big difference, right? The 7 versus 13, that's 6 billion people different. That's a very big difference. You may wonder, why is there such uncertainty in population? Because population is actually a very conservative thing, right? So you guys are in your early 20s. So if we wait 20 years, most of you will have had kids, right? That's a very easy prediction to make. And that means that in 50, maybe 60 years' time, most of you will be grandparents, right? So that is actually a fairly easy prediction to make. And see some of the people sort of like wincing, not me. But if we take a population average, then yeah, this is a fairly predictable thing. Similarly, we know we have very good life tables. We know at what age people tend to die. And that's slowly changing over time, but only slowly, right? So you may think this is an easy prediction to make, but it is actually not. The reason is that although fertility is falling everywhere, the speed at which fertility falls actually varies quite a bit. This low scenario, essentially what it does is it extrapolates the drop in fertility that we observed between 1990 and the year 2000 in Africa. And if that pattern continues, then there won't be a whole lot of, well, there will still be 7 billion people, but not nearly like 13. So that is where the low scenario comes from. But actually, if you look at a longer time span, say 1960 to the year 2000, fertility fell much more slowly in Africa. And if you project that trend, you actually end up in the high scenario. And then the question is, of course, is the recent trend more representative of the future, or is the longer trend more representative of the future? Unfortunately, the drop in fertility in Africa, sub-Saharan Africa, is still continuing, but it is slowing down again, right? So that is why the United Nations actually switched from this scenario as the best guess to this scenario as their best guess. Other people are saying they're too optimistic and should go to the high scenario. But there's a lot of uncertainty there, right? Second thing you're more familiar with, that is income, right? And projections of income. And you see the astounding range of uncertainty here. Also, the numbers are mind-boggling, right? So, the current average per capita income is around $7,000 per person per year. That was not a question. According to the most pessimistic scenario, that will triple to around 21,000. The average income on the planet, this is Greece, Portugal, right? This is a fairly well-to-do society. That's the world average. The high scenario will take the average world income to $140,000 per person per year, which is richer than Luxembourg, right? This is the Bahamas. It is very difficult to imagine a world where everybody is upper middle class, everybody is what we now would call upper middle class, right? But this is what happens if you just extrapolate growth trends, right? It's very difficult to imagine such a world, right? At the same time, if you think back to the year 1923, could you have imagined 2023? No. It's sort of, well, actually it's 80 years, right? If you go back to 1939, could you have imagined what the world would be like in 2023 and how rich we are? Even though you guys feel poor, you are so much richer than the average person was in 1940, right? So maybe this can happen, maybe it can't, I don't know. But this is the range forecast that we see. There is a peculiar thing here, and that is that we have 5 pronouncedly different scenarios for per capita income, and we have only 3 scenarios basically for population growth. And that is because this is not done with an integrated model. The people who generate the population scenarios don't talk to the people who generate the economic scenarios. And even though we have tons of empirical evidence as well as good theory to show that, yeah, richer people have different fertility and mortality patterns than poorer people, that feedback is not included in this particular set of scenarios. Now, the final 2 components, this is energy intensity. What we have observed, as I said, is that energy intensity, terajoule used per dollar value added, has fallen steadily over the last 40, 50 years. All these models project that will continue, some a little bit slower, some a little bit faster. Some people say that here they're really beginning to push the physics, right? There are sort of like, there is such a thing as thermodynamics and thermodynamic limits, but these are continue or likely to continue to fall. And then finally, how much CO2 comes out of generating this amount of energy. There you see very stark differences between the scenarios. And also something that I did not tell you, I sort of like, we're talking about the middle of the scenarios, and the middle is the median of the models, and the range that you see is the range of model results. And basically there is no range here, the models just all agree with one another, right? That's not because they agree, but essentially because they calibrate to each other, right? That's why there is so much agreement. Here the models are set free. You see this enormous range of results, right? Even within a scenario you have models strongly disagreeing. So what we've seen in the historic period is that energy intensity went the wrong way, went the right way, went the wrong way again, right? From a CO2 emissions perspective. Most scenarios are saying, well, we will continue to decarbonize the economy, even in the absence of climate policy. And that is because wind and solar are now just so much cheaper than they used to be. And in many places of the world, wind and solar are cheaper than coal and gas for making electricity. So that will continue to fall. Other scenarios basically say it will stay where it was, right? Sort of like an agnostic prediction. I don't know what way it's going to go, so I'm just going to keep it where it is. But there's also scenarios out there that actually increase the carbon intensity. And I will talk more about that next week. Essentially what is going on here is we're gradually running out of gas, we're gradually running out of oil, and in these scenarios we're going to go back to coal. So we're no longer going to make electricity from gas, but we're going to burn coal again. That is something that you know about. How do you drive a car on coal? Actually, the Nazis sorted it out, right? When the German economy was blockaded during World War II and the Nazis ran out of oil, they figured out how to liquefy coal in so-called Fischer-Tropsch process. And you can run a tank on that, and you can run a car on that. It's essentially diesel, right? The South Africans have further developed this technology when we blockaded them during the apartheid, the end of the apartheid regime. And now the Chinese, who are very worried about importing oil through the Straits of Malacca, which the US Navy can very easily block, have further perfected this particular industrial process. So we know perfectly well how to take coal, liquefy it, and run a tank or a car on that, right? So this is technically feasible, and this is what is going on in these scenarios. So you see this enormous range of results. You see this enormous range of results. No surprises here, right? We're talking about a world 80 years into the future, and it's simply very difficult to imagine what life would be like, what the world would look like 80 years from now, right? The only thing to do is always to look back at the science fiction writers of 100 years ago and how they imagined our lives would be. And they get some things right and some things completely wrong, right? And chances are that we're in the same situation here, right? That some of the things that are forecasted here will come to be, and others will be, in 20 years' time, we'll be looking back and laughing at this and saying, how silly were we then, right? So that's it for this week. Next week, I'm gonna take what we've just done and say, now we want to get rid of CO2, how are we gonna do it, right? Okay, I hope to see you guys next Wednesday.